Gravitational collapse of matter in the presence of quintessence and phantom-like scalar fields is investigated in this work. The authors propose a model that incorporates the principles of general relativity up to virialization, focusing on a spherical patch that undergoes gravitational collapse. The treatment is based on the top-hat collapse, where the dark matter sector collapses, while the dark energy sector maintains a profile similar to the background expanding Friedmann-Lemaitre-Robertson-Walker (FLRW) universe for suitable model parameters. The authors highlight that, in order to formulate the problem in a general relativistic setting, one must abandon the idea of a closed FLRW isolated collapsing patch. Instead, an external generalized Vaidya spacetime is matched with the internal spherical patch, guided by the FLRW metric. This approach shows that almost all collapses are accompanied by some flux of matter and radiation in the generalized Vaidya spacetime. Interestingly, some spherical regions of the universe are found not to collapse but expand eternally, producing void-like structures. The authors argue that the formation of structure in a homogeneous and isotropic universe is an evergreen topic in astrophysics and cosmology. In the standard picture, the seed for structure formation comes from linear perturbation theory, with some modes growing and entering the nonlinear regime, guided by Jeans instability and other effects. Gravitational collapse is assumed to be primarily driven by the dark matter sector, with the baryonic matter following the dark matter flow. The traditional top-hat collapse is modified to incorporate the effects of dynamic dark energy, modeled using quintessence and phantom-like scalar fields. The authors emphasize that previous attempts to study gravitational collapse in the presence of dark energy have been purely phenomenological, neglecting the principles of general relativity. In contrast, their approach addresses the energy conservation problem by matching the internal FLRW patch with a generalized Vaidya spacetime, predicting the emission of radiation from the boundary of the collapsing region. The model predicts that the collapsing dark matter cloud affects the dark energy density locally, forcing the dark energy sector to radiate. This approach is natural, as the effect of a gravitational collapse does not go unnoticed in the dark energy sector, which reacts by transforming locally into radiation. The authors note that their model is the first serious attempt to establish a formal general relativistic paradigm for the spherical collapse of dark matter in the presence of dark energy. However, they acknowledge that the relativistic formalism is not fully extended up to the formation of the singularity, as large-scale structures exist and are produced from some virialization process. In the context of a two-component universe, where dark matter and dark energy are the primary components, the total gravitational potential of an overdense region can be described by the equation Vt equals 1/2 integral v rho dm phi dm dv plus 1/2 integral v rho d phi d dv plus 1/2 integral v rho dm phi d dv plus 1/2 integral v rho d phi dm dv. This equation encompasses four distinct scenarios. 1. Dark energy has no influence on the evolution of dark matter overdensities. 2. Dark energy affects the virialization process but does not cluster or virialize with dark matter. 3. Dark energy clusters and does not virialize with dark matter. And 4. Dark energy clusters and virializes with dark matter. The authors of this paper focus on the third and fourth scenarios, where dark energy clusters and either does not or does virialize with dark matter. In the fourth scenario, the total potential energy of the overdense region is given by Vt equals 3m squared 5r 2 plus 3 omega m squared 5r r max caret 3 omega 1 plus 3 omega m squared 5r r max caret 6 omega. Using the virialization condition and the expression for the total potential energy, the authors derive a cubic equation for eta, the ratio of the virial radius to the maximum radius, 4q eta caret 3. A underscore max, caret 3, 1 plus omega, 2 eta, 1 plus q, plus 1 equals 0, where q equals 1 plus 3 omega, q, 2, with q being the ratio of dark energy to dark matter densities at the turnaround time. The authors also discuss the problem with the homogeneous dark energy model, where the background universe continues expanding after the virialization of the overdense regions, leading to a change in the dark energy density within these regions over time. This issue is resolved in clustered dark energy models, where dark energy clusters and virializes with dark matter, resulting in a constant dark energy density within the overdense regions. The research paper discusses the gravitational collapse of dark matter in the presence of dark energy. It presents an equation for eta, which is a measure of the gravitational potential energy, highlighting scenarios where dark energy can cluster and virialize inside overdense regions. The paper also explores the dynamics of a perfect fluid made of dust-like matter and a scalar field, using a two-fluid model to describe the structure formation of dark matter. The authors consider a closed FLRW spacetime for the overdense region and a flat FLRW spacetime for the background. They use Vaidya spacetime to describe local dynamics around the boundary of overdense patches. The paper's main focus is on the allowed parameter space for the overdense region to collapse in the presence of quintessence-like and phantom-like scalar fields. Figures and equations are used to illustrate the concepts and demonstrate the calculations. The research aims to understand the structure formation of dark matter in the presence of dark energy, providing insights into the evolution of the universe. The research paper discusses the dynamics of a two-fluid system, comprising a matter field and a scalar field, within the context of a generalized Vaidya spacetime. The authors investigate the variation of different variables with respect to time, focusing on the quintessence field. They explain how the flux of the scalar field from the internal spacetime gives rise to non-zero components of the energy-momentum tensor of the external spacetime. The paper highlights the significance of the scalar field in generating non-zero pressure at the boundary, which in turn influences the matter flux. The authors also discuss the virialization process of the two-fluid system, considering the matter part to evolve like a closed dust ball while the internal density of the scalar field remains almost constant. The paper's findings emphasize the importance of the scalar field in shaping the dynamics of the system, particularly in the context of quintessence. In the context of a Friedmann-Lemaitre-Robertson-Walker (FLRW) spacetime, this section delves into the gravitational collapse solutions for matter in the presence of quintessence and phantom-like scalar fields. The effective density and pressure of the resultant fluid are derived using Einstein's equation, resulting in equations 31 and 32. By utilizing these expressions, an equation for the scalar field energy density is established in equation 40, which involves the potential of the scalar field V phi and the fluid energy density ρm. The second-order differential equation for the scalar field, given by equation 42, is obtained through a series of manipulations involving equations 35, 36, 37, 38, and 39. This equation is crucial for understanding the dynamics of collapse and is solved by choosing a specific form for the potential V phi equals V0 e caret elf, where V0 and lambda are constants. The fluid energy density ρm is assumed to be proportional to a caret 3, reflecting the dust-like nature of matter. The curvature of 3 space K is set to 1, indicating a closed universe. The analysis also includes the presentation of numerical results in Figure 6, which demonstrates the variation of different variables with respect to ρm0 for the quintessence field. The plots depict the evolution of the scale factor A, the equation of state parameter OFF, the ratio of scalar field energy density to the fluid energy density, and the total equation of state parameter omega t over time. These results provide insights into the role of quintessence and phantom-like scalar fields in the gravitational collapse process. The study highlights the importance of the interplay between the scalar field and matter in determining the collapse dynamics. The choice of potential and the initial conditions significantly influence the behavior of the system, leading to different scenarios for the collapse. The paper emphasizes the need for further investigation to understand the implications of these findings on the formation of structures in the universe. Here is a combined summary of pages 11 and 12 of the research paper. The authors present a two-fluid model to study the dynamics of an overdense region in the presence of a quintessence-like or phantom-like scalar field. They derive a set of differential equations governing the evolution of the scalar field and the scale factor. The solutions to these equations are obtained by considering two initial conditions, and the resulting dynamics are analyzed for different values of the model parameters v0, ρm0, and lambda. For the phantom-like scalar field, the authors derived two differential equations, one for k equals 1 and another for k equals 0, which describe the dynamics of the resultant fluid in the overdense region and the background, respectively. They solved these equations numerically, using initial conditions phi a equals 1 equals 0.001 and phi a equals 1 equals 0.00001, and explore the parameter space of v0 and ρm0 that allows for an initial expansion phase of the overdense region, followed by collapse. The authors show that, depending on the values of v0, ρm0, and lambda, the overdense region may reach a maximum physical radius and then collapse, leading to a spacetime singularity. To stabilize the system, they invoke the Newtonian virialization technique, which is commonly used in the top-hat collapse model. In the next section, the authors demonstrate that the scalar field behaves almost like homogeneous dark energy in their model, allowing them to use the virialization radius calculated in section 2. They present plots of various dynamical quantities, such as the scale factor A, the equation of state of the scalar field OF, the density ratio ARF, and the effective equation of state omega t, as functions of time for different values of v0. The authors highlight that, for a fixed value of ρm0, there exists a v0 such that for all values of v0 less than v0, the overdense region can have a collapsing phase after the initial phase of expansion. Similarly, for a fixed value of v0, there exists a lower limit ρm0 for a fixed value of v0. Therefore, one cannot consider arbitrarily large values of both v0 and ρm0 to model a top-hat collapse-like dynamics. Instead, suitable small values of these parameters must be chosen. The plots of the dynamical quantities show that the density ratio ARF slowly increases with comoving time and stays close to 1 throughout the total evolution of the overdense region, indicating that the quintessence-like scalar field in the model approximately behaves like homogeneous dark energy. The research discusses the dynamics of a two-fluid system consisting of pressureless matter and a quintessence-like scalar field. It examines the variation of different variables with the scalar potential V, phi, equals V0 E minus ELF for phantom field. The study focuses on the behavior of the scale factor A, the equation of state OF, the density of the scalar field ARF, and the total equation of state omega t. Figures 8 and 9 show the variation of these variables with the variation of lambda and ρm0, respectively. The results indicate that the system approximately resembles the homogeneous dark energy model, with the ratio ARF, ρm0 approaching a constant value and OF tilde operator -1. The study also discusses the top-hat-like collapse in the presence of quintessence or phantom-like scalar fields, highlighting the similarities with the homogeneous dark energy scenario. The findings suggest that the system's dynamics are influenced by the scalar field, leading to a longer time interval for the overdense region to virialize compared to the top-hat model. This paper explores the gravitational dynamics of a two-component system consisting of pressureless matter and a scalar field, with the scalar field representing dark energy and the pressureless matter representing dark matter. The authors have chosen a closed FLRW metric as the internal spacetime for the overdense region, seeded by the two components, and a flat FLRW metric for the background spacetime. The model predicts that some regions in the universe will collapse gravitationally, while others will expand eternally to produce voids, depending on the potential parameter V0 and the initial value of the local dark matter density ρm0. The nature of the outgoing flux in the Vaidya region depends on whether there is a collapse or an expansion. The authors discuss their model qualitatively and do not attempt any comparison with observational data. They also plan to work on the observational side of this problem in the future.